modeling their impacts and radiation budget, atmospheric temperature and climate using radiative transfer and general circulation and global climate models. He was a lead author of the 2007 Climate Science Assessment of the Intergovernmental Panel on Climate Change, IPCC, which shared 2007 Nobel Peace Prize. He is a reviewer and an author on the World Meteorological Organization, WMO, scientific assessment of ozone depletion. He was a senior fellow at the Institute of Advanced Sustainability Studies, Potsdam, Germany in 2019. He was a senior fellow at the NASA Ames Research Center, California during 2008 and 2011-12 under the NASA postdoctoral program. He is a recipient of the Indian National Science Academy INSA Young Scientist Award in 1997 and also the NASA Group Achievement Award in 2009. He has published about 100 research papers in peer-reviewed journals. He recently authored as a textbook entitled Atmospheric Aerosols, Characteristics and Radiative Effects. And detail about Professor Ramchandran can be obtained at his homepage at PRL. I request Professor Ramchandran to deliver his webinar. Thank you.
Thank you, Dr. Sinha. Dear friends, good afternoon. At the outset, I'd like to thank Professor Chandrasekhar and Dr. Sinha for the invitation. While I accepted the invitation with a little trepidation because it was written to whom I will be addressing. So that actually posed a challenge to me because normally you go deliver a talk based on your expertise and then try to come out of it when the job is a little easier. But when the audience or the clientele is going to be of various kinds, and some of the brightest minds in the Indian engineering force, which includes also science background people. So I set out a challenge for myself to kind of do the reverse engineering and then try to attract and then make you understand the various concepts of what we know on aerosols, which includes the physics, chemistry, maths, biology, and the engineering aspects. So with these words, let me begin. So the presentation will go in the following sequence. I will begin with an introduction, and then I will discuss the various features under the PCMB and E, and then finally we'll conclude the talk. So these aerosols or air pollutants, as we know, are the solid or liquid particles that are suspended in the medium of air. They can be of natural and anthropogenic origin. You can see that the sources are different, the shapes are different, the structures are different, etc. So as all of you know, that the Earth's atmosphere is a nitrogen-oxygen dominated atmosphere with 99% of the volume being occupied by these two gases. In the remaining 1%, all the other species, all the other trace gases actually fight for each other. Why? For their attention. Starting from argon, carbon dioxide, ozone, trace gases, and aerosols. If you look at this, the percentage contribution to the total volume of the constituents in the Earth's atmosphere by aerosols is on the order of about 0.1% or so. Despite their very small contribution in the total volume, they play a very important role in the physico-chemical process and the dynamical and radiative aspects of the Earth atmosphere system, as you will realize at the end of this seminar. So the sources of these particles are primary and secondary. The primary sources are the direct sources, which are oceans, deserts, terrestrial biota, meaning biological material of plant origin, smoke from burning of land biota, direct anthropogenic particle emissions, terrestrial ejecta, which includes the volcanic eruptions or the effluvia from volcano, meteorites, the extraterrestrial and the interplanetary dust also form a part of the aerosol. The secondary or the indirect sources are the major source of particles for smaller in size, which also contribute to air pollution, which is mainly due to the gas to particle conversion mechanism. The precursor gases get converted into aerosols and then remain as aerosols in the atmosphere. 99.99% of aerosols or more are located in the 0 to 40 kilometer altitude of the Earth's atmosphere. The extraterrestrial and the interplanetary dust contribute to altitudes to aerosols above that, but as you can see, they are a minuscule, very minuscule portion of the total aerosols that is present in the Earth's atmosphere. And second thing, these emissions from the meteorites or extraterrestrial dust or the interplanetary dust are kind of not systematic. They come in kind of in events, and so to the total volume or the net volume of aerosols that is present always in the atmosphere, these are like very, 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 very small. So, so that you can appreciate the kind of concern and what are we studying with respect to the aerosols and the air pollutants that we know, I have tried to compare the particles that we call as aerosols with the known species that we are aware of. For example, human hair is shown here, typically a dimension of about 50 micrometer in diameter. When compared to that, even the dust and the other biological material are all particles that are smaller than 10 micrometer. And the particles such as soot, organic carbon, other metals, etc., they are even smaller than 2.5 micrometer. This is just to show the level of the size of the species and how they are playing an important role in the atmosphere. So these aerosols also serve as the cloud condensation nuclei. The smaller particles that are present, they can condense on the vapor, and then they nucleate to form bigger particles, which then finally turn into cloud condensation nuclei about 100 nanometer size. Please note that there will be no clouds if there are no aerosols in the atmosphere. So this is an important aspect of the Earth's atmosphere where aerosols serve as the cloud condensation nuclei, which includes sulfates, organics, etc. Now, one aspect that manifests itself because of aerosols is what is called as the visibility or the visual range. We know that when there is more pollution or dust in the atmosphere, the visibility reduces. Here I have just put a figure here just to illustrate the difference between a cleaner environment and a polluted environment. So this is a kind of effect that it has on the visibility. So this is a kind of a nearby manifestation of these particles when you are in a cleaner place with respect to a polluted place. So to sum up in the introduction, these aerosols are ubiquitous and omnipresent around us and is involved in almost all the processes that control the Earth's climate, starting from affecting the balance of radiation, cloud formation, precipitation, emissions, getting transported, the physics, chemistry, and all of them. So each of this we will kind of look at it in some detail, and I will try to also demystify the myths surrounding these particles in the atmosphere. So the aerosols, we saw that they come from different sources and they are of different sizes. Here I have tried to plot as a function of radius, the type of particles that you can have in the nucleation size range, meaning particles that are less than 0.1 micrometer in diameter. So this is roughly 1/100th of 2.5 micrometer kind of a scenario, 1/10. And then you have the accumulation size range, which is between 0.1 to 1 micrometer, and then the acquired size range where the particles are larger than 1 micrometer. So different processes take place in terms of the formation. Like I mentioned earlier, that when it forms the cloud condensation nuclei, it is the vapor condensing on the smaller particles. They form a chain of aggregates and then form the aerosol particles in the nucleation size range, which then they chemically can convert into low volatility vapor or aerosols through nucleation and also the condensational growth. They can form little bigger droplets than which are in the nucleation size range. And then they are the main amount, they contribute the main amount of particles in the accumulation size range. Well, particles that are larger than 1 micrometer in the atmosphere are generated by mechanical process such as wind-blown dust, sea salt, sea spray emissions, volcanoes, plant particles, etc. All of them we'll see in detail as the talk progresses. So when I mentioned that it involves all the aspects of science and also engineering, so I meant this one. So the size, shape, and the structure of these particles, they vary. The formation mechanism determines the physical characteristics, while the production source, whether it is coming from a vehicular emission versus a volcano versus a wind-blown mineral dust, that determines the chemical composition of the species. Then both of these combined, the composition, size range, and the shape decide the ability of each particle to interact with the electromagnetic radiation that is coming from the sun and also going back from the Earth's atmosphere. So directly contributing to climate and the radiation. And we need max in order to determine the source strength of each of these components in the Earth's atmosphere, which is decided by the mass of these particles and also the number of these particles as a function of size. So starting from sea salt, I'm sure I don't need to tell my friends in Trivandrum that have you seen sea salt or sea spray? Well, they will kind of look at me. So the sea salt is produced from sea spray on the sea surface due to winds. Thus, the production of these particles depends on the wind speed. Typically, the injection of sea salt particles into the atmosphere occurs from bursting of air bubbles via jet and film drops. This production of these particles occur when free energy of the collapsing pull particle gets converted into kinetic energy. The number of film drops that come out of this depend on the size of the bubble. The bigger the bubble, more the number of film drops. So usually when the wind speeds exceed more than 4 to 5 meters per second, you see on the ocean surface a kind of a white layer, which we call as the white caps, which are formed by wave breaking due to winds on sea surface. They produce a large number of bubbles. These start appearing when the wind speeds exceed about 4 meters per second. So this is how the sea salt particles in the atmosphere are produced. The second dominant aerosol component, namely mineral dust, they originate from deserts, dry lake beds, semi-arid regions, in addition to drier regions where the vegetation is reduced or from soil surfaces that are disturbed by the human activities. So the dust particles are essentially produced by chemical leaching of water-soluble components on crustal materials such as rocks and stones. Where they are produced, and because these get transported, like you can see on the figure on the left hand, from the figure on the left hand side, the distribution goes on changing when depending on the soil texture and the wind speeds. Thousands of kilometers away where they originated, the dust particle gets shifted to smaller sizes. So here, to give an idea of what we are talking about in terms of the size, near the source, a source soil, where suppose if I am allowed to measure the dust here, the size will be about 25 micrometer, and then a little above ground, a little farther, then you can see the size that is getting reduced, and regions thousands of kilometers away, they can be very, it depends on how high is the wind speed, what is the texture of the dust material, etc. So you can see particles that are very small, at thousands of kilometers away from the desert regions. Then the other major aerosol component in the Earth's atmosphere is the sulfate. All the sulfur that is present in the Earth's atmosphere ends up as sulfate, as it is the thermodynamically stable form of sulfur. It interacts with oxygen and then forms the sulfate, out of which the marine flora and the terrestrial biota are the major biological sources of sulfate aerosols, meaning dimethyl sulfide and other compounds. The only non-biological source of sulfate in the atmosphere comes from volcanoes. And these are all the natural sources. While the fossil fuel and the biomass combustion and the biofuel burning, which is anthropogenic in nature, they inject a large amount of sulfur dioxide and then sulfate particles. So typically the sulfur dioxide that is emitted and other species such as carbon disulfide, etc., they get oxidated to carbonyl sulfide. SO2 can get directly converted into sulfate, while carbon disulfide and carbonyl sulfide, they get converted into sulfur dioxide first, and then they become sulfate aerosols. This is a schematic of aerosols that is found in the troposphere and in the stratosphere of sulfate. And through this process occurs through gas to particle conversion mechanism, which we saw earlier. Now, the other natural component that is present of aerosols in the atmosphere is of biogenic or biological origin, where the bacteria, viruses, plant and animal debris, pollen, fungal spores, etc., they also contribute to the aerosol that is present in the Earth's atmosphere. I have shown here an illustration of the typical sizes of pollen grains versus the other species of interest. So typically the forest regions and the soils, from there they emit a large amount of these biological particles, which also play a role in the cloud condensation nuclei process that we talked about earlier. And then they also get transported across depending on the wind speed, the conditions that are favorable, etc. So you see on the right hand side a word called brochosomes. These are intricately structured microscopic granules that are secreted by a species called leaf hoppers. These are also aerosols practically suspended in air. Liquid or solid is what we call as the aerosol. However, when it comes to the radiative aspects and the climate aspects, etc., the biological aerosols have their own role in terms of the climate change, etc., which we will touch later. But when it comes directly to radiative effects on climate, the other aerosol species that we talked about earlier are the aerosols from the different sources. They contribute to those effects. The other major species of aerosol is a nitrate. This nitrate is formed as an end product of reactions involving trace gases produced either naturally or by human activities in the atmosphere, typically nitrogen oxides, volatile nitrogen-bearing gases, and gaseous nitrates, which are precursors for the nitrate to be found, which are also both of natural and the anthropogenic origin. The vegetation and the soil and the fertilizers that are used, they inject a large amount of these nitrogen oxides, and the vehicular and industrial emissions also inject a large amount of nitrogen oxides and volatile nitrogen-bearing gases. The other species that is gaining interest in the recent decades are the carbonaceous particles, which are of two types. One is the black carbon and the other is organic carbon. Black carbon is emitted as primary particles from incomplete combustion process, such as fossil fuel, biofuel, and biomass burning. Organic carbon is emitted as both primary particle and by secondary oxidation from volatile organic compounds, which may have their origin of the biological origin via condensation. Now, the primary organic carbon comes from the anthropogenic, namely fossil fuel and biomass, and also from the natural sources, namely plant debris, pollen, spores, algae, etc. Typically, oxygen and hydrogen and other chemical species are usually associated with the organic carbon that is present in the Earth's atmosphere, and in toto we call them as organic matter. As opposed to all the other species in the Earth's atmosphere, there are no natural sources of black carbon in the Earth's atmosphere. So almost all of them that is present, black carbon in the atmosphere, is actually human produced. So if I'm allowed to look at break up the budget and see that how much it is natural, how much is man-made in terms of the aerosol loading or the source that is over the Earth's atmosphere, then we put it in terms of 10 to the power of 12 grams per year. This is the source, the amount of emissions per year. And then we try to put the numbers based on various other estimates and model studies. And we try to categorize them as natural versus anthropogenic. The natural, which I have categorized as dust and sea salt, they contribute more than 90%, while the man-made contribution is only about 5% or so in the total volume of aerosol that is present in the atmosphere. But the whole scenario you will see will change when we are talking about the radiative and the climate aspects. So these aerosols, which are produced from different sources and can be categorized as sea salt, mineral dust, sulfate, nitrate, black carbon, and organic carbon, they produce a kind of a hazy atmosphere which is clear, and also this is a familiar picture across the Indo-Gangetic plain during the winter time frame, and there is a lot of these aerosols get transported across, and from all these both natural and anthropogenic sources. You also notice that when I am classifying them as natural versus anthropogenic aerosols, the natural aerosols are more whitish when compared to the anthropogenic sources, which are blacker, the importance of which will come in the next few slides. Keep this in mind. So these aerosols that are produced from different sources can produce local, continental, regional, and global distributions, and hence can contribute to global effects. So when physics and chemistry came in, Max, how can it be far behind? So Christian Junge was the first scientist who found that in order to represent the aerosols of different sizes, you need what you call a size distribution function and an expression to derive or to measure the size distribution function. Because this became important because unlike the air molecules, which is of one size, aerosols are of several magnitudes. They are different, sweeping from a cluster of molecules at one end to hailstones at the other end. So you need to have a mathematical measure to illustrate how the particle numbers vary as a function of size. So Junge thought of an easy way to come out of this. He simply said, okay, the number of particles that are present should be proportional to a parameter which is called as the size distribution function, which is given as mu here. And depending on its variation, the number of smaller or the larger particles will be different in the atmosphere. Now, one of the major drawbacks in this distribution is that this may be applicable to kind of one type of species, one type of particle, namely sulfate, nitrate, or black carbon or something. But when the atmosphere, which has all the components that are present together, then it becomes difficult to categorize this using this size distribution. So then came what is called as the log normal, the normal distribution with a log attached to it. So this one has the ability to decipher or delineate the contribution from each of the different types that contribute to the population that are present in over a particular region. So here what we are seeing is an aerosol distribution for an urban region, which is primarily made up of three components, namely the insoluble species, certain amount of organics and dust, soil dust particles, Water soluble is sulfate, nitrate, etc., organics, etc. And black carbon is the human influenced or human emissions of black carbon from industrial and vehicular emissions. So each of these components, I have named it as 1, 2, 3, and the total is given in red. They all have a distribution with the different values wherein they actually peak and they contribute to the total. So this is a kind of a more realistic way of representing the aerosol distribution, which arises due to aerosols of different sizes that are present in the atmosphere and in different numbers. It is not the same, but the numbers are also different. So you can equally represent the number that is measured or derived into area and volume by multiplying spherical 4 pi r square and 4 pi by 3 r cube. So depending on the r square r dependence, the peak at which the distribution peaks also will differ because the area is r squared and volume is r cube, as you are aware. The aerosols that are produced by different processes and the different sizes, their residence time in the atmosphere also vary as a function of size, shape, and altitude. Typically, you will have something like 10,000 particles per centimeter cube in the surface, and then as you go up in the atmosphere, it will start decreasing. So when you go to the boundary layer, that's roughly about 3 kilometers or so, you can see a large difference or decrease from 10,000 to about 500 particles, and you go up a little further to free troposphere, which is about 5 or 7 kilometers, then the number of particles will decrease, and you still go further. Stratosphere, for example, about 17 to 20 kilometers, and above, the number of particles will become even smaller. So on the x-axis here is the radius of the particles. What you can see is that as a function of altitude, the size of particles that are present also keeps varying because of the process that are present here. Typically here in this small size range, the residence time is on the order of a few hours to a day, and then they convert through gas to particle conversion into particles that are in the accumulation or condensation size ranges, while the particles that are larger than 1 micrometer or so, they feel the effect of gravity more effectively than the particles which are of smaller size, as you know. So they also settle out of the atmosphere in a few hours to 1 day's time. It is the particles within the size range of about 0.01 to 1 micrometer or less than 10 micrometer. They can stay a little longer than the particles that are smaller or bigger than this range. And even these will, the sizes will change as you go up in the Earth's atmosphere. And the other major difference between the aerosols that are present in the troposphere with respect to stratosphere is that in the troposphere, you can see all kinds of these particles that we saw before, but in the stratosphere, 99% or more are only sulfate particles that are present. So when the electromagnetic radiation interacts with these particles, for example, with an air molecule, we know that the interaction can be simply calculated as due to a dipole scattering, where the radiation that is scattered is equally distributed in both forward and backward direction. So it's a kind of a symmetric scattering that happens. But in case of an aerosol, for example, when the particle size is of the order of about 0.1 micrometer, you will see a large forward scattering when compared to the air molecule, which is symmetric. And when the size increases further, the amount of light that is forward scattered will also be higher. When compared to the air molecule, the intensity that is scattered by aerosols in the perpendicular and parallel directions, they are a little more complicated to derive using, for example, we use Legendre polynomials of argument n and order n and argument cos theta, where an and bn are the constants, So we calculate the amount of radiation that is scattered as a function of size and also as a function of the refractive index. Why refractive index we'll see in the next slide. From that, what we get, we calculate the extinction, which is the summation of scattering and absorption, and then calculate the scattering, and then the difference between scattering and the extinction gives rise to the absorption. So all these particles that are produced by different sources, different types, they can actually scatter and absorb the radiation. So each of the particles that you see in the atmosphere is characterized by a refractive index, including the air molecule. But which has a real and an imaginary part, as you are aware. The real part signifies the scattering contribution, while the imaginary part indicates the absorption contribution. The absorption contribution of air molecules is almost nil, so the refractive index, imaginary refractive index is small. So here, for example, I have shown the scattering efficiency, the extinction efficiency of particles, scattering and the absorption efficiency. For example, let us focus on sulfate and black carbon. Sulfate, for example, the imaginary part is 1 × 10⁻⁻8. For black carbon, it is 0.44. You can see that in the case of sulfate, there is no absorption that is contributing to extinction, while in case of black carbon, it is the absorption that is contributing to extinction. So once we know how much is getting scattered, how much this particle of this size is absorbing, then we can, with the number of particles that is present that we know, we can fuse the size distribution and the scattering efficiency of these particles to derive the extinction efficiency or extinction coefficient. And how much of this radiation is forward scattered or how much is backward scattered is calculated by using the aerosol phase function. So you can see that there is a large amount of forward scattering that happens initially in the first few degrees, and then it also changes as you go to the back sphere. The aerosols do not necessarily exist as individual components in the Earth's atmosphere, such as sulfate separately versus black carbon separately. They can also be present mixed in the atmosphere. And one of the scenarios is actually a simple scenario, which is external, while the other scenario is a little more complicated, which is either the core shell or the homogeneous internal mixing. In core shell, one species forms the core and the other species acts as a shell. And in the homogeneous internal mixing, all the species kind of get mixed together and form one single entity. And they can be of different shapes also, depending on the process that they are produced and the types of particles that are emitted. So, and they can be of different sizes, as it's also shown here. So this has a direct linkage to the phase function that we derive. Depending on the shape of the particle, the phase function will also keep changing. So in different environmental settings, how these particles will be different. So we come back to the aerosol distribution, the urban distribution, which we saw. We know that aerosols over urban regions are mostly from gas to particle conversion and combustion, mainly anthropogenic. And typically particles in the fine mode, meaning less than 1 micrometer, are much, much larger than when with respect to particles that are larger than 1 micrometer. And typically the aerosols over the urban regions, especially in the fine mode, are about more than 1 order of magnitude when compared to a clean continental or a background or a marine region. But when you go to marine region, for example, you will see that the particles of bigger sizes, the sea salt particles, are typically larger than the urban fine mode species. So to kind of re-emphasize the aspect that depending on the environment and the chemical makeup of these particles, the sizes, the numbers, and the mass can vary. So if you look at the radius, for example, from the urban to desert, just like fine to coarse mode, you can see that the radius of the particle increases. Typically, the mass and the numbers also change accordingly. So Once we know the physics, chemistry, and the fundamental principles of how these aerosols work, then we resort to developing the instruments, which can be ranging from a very simple method of just collecting the air on a sample and then trying to analyze using a high volume sampler, and then further with chromatography techniques, etc., to identify the species that is present, or use the principle of fluid dynamics and then the principle of impaction to derive the size distribution of the particles, to a very, very sophisticated mass spectrometer where you can actually derive both the size and the chemical composition of the particle, to obtaining a vertical profile of the aerosol particles, use the laser, which we call as the laser radar, light detection and ranging, similar to the radio detection and ranging as LiDAR, where you send a laser pulse into the atmosphere, typically in the mid-visible, and then you collect the scattered intensity as a function of altitude, where you can actually map the vertical distribution of these aerosol particles. Or the most simple technique, which is the sun photometer technique, which measures the columnar amount of aerosols present in the atmosphere through Beer-Lambert's law. And of course, for a global picture, global scenario, you need to resort to satellites. Currently, for example, there are several of them to measure the aerosol column, size and composition, which includes the MODIS and MISR. I'm sure you are aware of these satellites and the payloads in it. And then the different platforms that we use, starting from ground-based to go on ships, on aircraft, on balloon and rocket. We use a variety of them, and in space, of course, as we saw before, to characterize, measure, and sample these species for which the characteristics that you are interested in studying, for example, whether it is a surface, vertical, or the column, they matter, whether as a function of wavelength, altitude, etc. Depending on that and the characteristic of interest, the techniques vary. So, having talked about the different characteristics and the measurement platforms, the techniques that we can use to derive or measure aerosols, let us look at some of the features of the aerosol species. One is there are three parameters that describe the aerosol in whole, which is the optical depth, the columnar distribution of the aerosols in the atmosphere, the single scattering albedo, which is the ratio of scattering to extinction, which is the summation of scattering plus absorption, and then the asymmetry parameter, which is dependent on the shape of the particle. How much is the radiation that is forward scattered versus how much is backward scattered, etc. So if you look at the values, for example, sulfate being a perfect scatterer, the single scattering albedo of sulfate is actually 1, because there is no, as we saw in the figures that when we are looking at the scattering and the absorption contribution, the extinction is entirely by scattering in sulfate versus the extinction is mostly by absorption in black carbon. So you can see the single scattering albedo is a perfect 1 for sulfate and sea salt, while black carbon is the single largest absorber of solar radiation in the Earth's atmosphere. In a similar way, we can also see that the asymmetry parameter, which is the measure of the scattered intensity of the angular radiation, you can see that for particles that are bigger in size, for example, mineral dust or sea salt, the G values are higher when compared to the black carbon, which are mostly in the fine mode species or small size particles. So over different environments, how these optical, how the aerosol characteristics will vary. Here I have shown as an example or 4 different locations, which is urban, oceanic region influenced by biomass burning versus a mineral dust region. So the optical depth, the column content is higher for desert dust, regions influenced by desert dust, more number of particles. While if you look at the single scattering albedo, when the region has a mixed influence, such as for urban region, which has a lot of sulfate, carbon, black carbon, etc., the single scattering albedo is lower than 1. And when you look at the asymmetry parameter, you can see that the oceanic region has the biggest, highest G value when compared to what is present over the urban or the biomass burning regions. Typically, the particles are in the fine mode, so the asymmetric parameter are also small. As we saw that these aerosols are distributed across from the Earth's surface to 40 kilometers, if you do a kind of a slab or layer AOD, then you see that most of these are present in the first 5 kilometers in the Earth's atmosphere. But the scenario will change when there is a volcanic eruption, as you will see later. So almost 95% of these aerosols that are present in the altitudes of 0 to 5 kilometers, they are the most major contributor to the aerosol optical depth. On a global view of this same species, the aerosol optical depth, you can see that it is not uniform across the globe, and it also exhibits seasonal and spatial variations. So you also see the effects of transport over the during the monsoon months when compared to winter or pre-monsoon over the African region because of biomass burning, etc., which we saw in the previous transparency. The southern oceans, for example, the wind speeds when they are little higher, which are typically characterized by wind speeds that are greater than 10 to 15 meters per second, they produce a lot of sea salt, and hence sea salt AOD, which you can see in these global maps here. So while this figure gives the total amount of aerosols that is present, how they are chemically distributed, what is the chemical composition, what is the single scattering albedo, which is the ratio of scattering to extinction, you can see that the more they are redder means they are absorbing, while more bluish indicates that they are scattering time. So we can see that regions that are influenced by urban industrial emissions, biomass burning, etc., these are regions when the single scattering albedo is redder, meaning these aerosols are more absorbing when compared to the scattering type. And okay, now I just wanted to show that as an illustration that the life of an with aerosols, for example, there is no dull movement at all in life. So here what we'll see is a simulation of various aerosol species on a global scale. This will run for about 2 minutes, but I will keep talking in between. So you have dust in brown color, green, darkish green is the organic of the black carbon, sea salt is in blue, and kind of white to gray is actually the sulfate extinction. Now let me play the movie. Sorry, let me go back. So I'm playing the movie separately. So so what you are seeing here is that you can see that all aerosols of all kinds, different kinds, they are spread across the entire globe, and they keep changing. You can see the variation in time as you as the time is changing. You can see the types of particles are also changing. For example, let us just concentrate around the Indian subcontinent. You can see yes.
Any movie, sir? Could you please?
Really? Okay. Okay. Just a minute. Now can you see?
Not yet, sir.
No, I'm sharing the screen.
Okay.
Are you seeing now?
No, sir.
What about others?
Only folder is visible here.
Oh, really? Okay.
You have to reshare it.
Okay. Let me stop sharing and I will now share.
Yeah. Yeah, it appears. Now you can play it. Yeah.
Now can you see?
Perfect, sir. Perfect.
Okay.
Again, it's
Okay. Okay. So what we are seeing is the across the globe, aerosols of different types are produced and they are getting transported across. So if you concentrate just looking over the Indian region, you can see now it is approaching to March, April, May. You can see a large amount of dust particles that is coming from the desert regions, the arid regions that are surrounding. And you can also see the pattern that is changing. During monsoon, you will see a lot of sea salt that is sweeping across the Indian subcontinent. We are still in April. So you can see across the other regions of the globe, you can see the southern hemisphere, for example, it is a large amount of sea salt through the gusts of wind. You can see the sea salt that is being produced. And so it is a very active and a dynamic system of aerosols being produced over a certain location and they getting transported across. So at any given location, the characteristic of these particles will exhibit a change as a function of time, day, month, and season, and also interannual. So now the monsoon has started. So you can see that the whole, it's a kind of a white to green to a blue over the entire Indian subcontinent. Large amount of sea salt, dust, and the local production also contributes to the extinction here. And then in about, so this is still, we are in August. And you will see signatures of transport of from the African and the Southern American regions that we saw in the previous figure. So now we are going to be in post-monsoon now. You can see that actually suddenly India will become kind of cleaner. You can see the entire map of India that is visible now with less aerosols because the monsoonal precipitation, because of precipitation, the aerosols have settled or gone out of the atmosphere. Okay, now we looked at the physical, chemical, maths, biology, all these species. Now, why we should study? Why are they important in the Earth's atmosphere? So depending on whether these particles are scattering or absorbing, the effects on the atmosphere will also vary. So when it is scattering aerosols, for example, in both the cases, please note that both absorbing or scattering aerosols, the amount of radiation that reaches the Earth's surface will all be decreased, will be lower. Hence, both of them will produce actually a cooling. But later, the sulfate or the scattering aerosols will actually contribute to localized cooling as well as a cooling that spreads across the region and as a function of the altitude. While in case of absorbing aerosols, initially there will be a gradient because it is cooling at the surface and warming at the higher altitude, but this will homogenize because of mixing both in terms of vertical and horizontal scale, and then will actually contribute to warming. In addition to the direct effects, as we also saw earlier, that aerosols contribute to the formation of clouds, and depending on the nature of these particles that is present, When I say nature, it is the chemical nature of the particle and also the number that can be present between a cleaner and a polluted environment. The dust, the cloud characteristics of the properties and the lifetimes also will change. So between a cleaner environment and a polluted environment, the size of the cloud droplets you can see, which is shown in blue circles, they actually reduce, and you can also see more red drops, which are the aerosols. This can modify the optical properties and lifetimes of clouds, and if these aerosols are of the absorbing nature, then it can actually burn off the clouds, and then hence the evaporation can reduce. In addition, these aerosols form an important part of the global biogeochemical cycle. So when we say biogeochemical, anything that is a component of the Earth's atmosphere contributing to changes in terms of the biological, the chemical, and the geological contribution or changes in the system that contributes to biogeochemical cycle. So here, for example, the life cycles of most of these aerosol species present, namely be it carbon or sulfate or nitrate, etc., they all contribute to the geochemical, biogeochemical cycle. So we know that the atmospheric concentration of the gases have been increasing substantially during the industrial era, which we call as a global warming. Ozone, as you are aware, absorbs the ultraviolet radiation. It plays a key role in the biosphere and also in the budget of the middle atmosphere. It protects the harmful ultraviolet radiation. And then the biological process, wherein the biogeochemical cycle comes, the changes in the soil, vegetation, oceans, or anthropogenic activities, and the emissions coming from this, namely the fossil fuel, the fossil fuel and biomass consumption, changes in the land use, etc., they all contribute to changes in the climate. So directly and indirectly, aerosols form a part of this biogeochemical cycle. The next connection comes from the amount of dust that gets transported to the ocean. The dust is an important source of iron in the ocean. Now, this one, it depends on the kind of scale of parameters that are involved, which includes the atmospheric aerosol loading, the state of climate, the changes in the land use, and the dust that comes out of it, and the marine productivity. All of them are closely coupled. So you can see that the aerosol forms an important link in the entire biogeochemical cycle. Alteration or changes in any of these to the climate or to marine productivity or land use can influence the other aspect, other module, and then can contribute to climate and the climate change. So one of the last aspects regarding aerosols is the aerosols that are emitted from the volcano. Volcanic eruptions usually inject tens of megatons of sulfur dioxide into the stratosphere, altitudes that are above 15 to 17 kilometers, depending on the magnitude of the eruption. It also injects carbon dioxide, water vapor, etc. But these are very small quantities with respect to the amount that is already available in the Earth's atmosphere. But the sulfur dioxide gas that is ejected, which later forms into sulfate aerosols, they are a huge amount of contribution, addition to the already existing aerosols present in the Earth's atmosphere. Now, these aerosols, once they are produced, the sulfate aerosols, which are projected like a fountain effect, when they go to stratospheric altitudes, because these we have seen, they can scatter the incoming shortwave radiation. They block the radiation that is coming in, hence they will produce a cooling at the Earth's surface. But in terms of the long wave, wavelengths above 4 micrometer, these very aerosols can absorb the Earth emitted long wave radiation. And hence, they produce contrasting results in the troposphere and in the stratosphere. In addition, which is one of net cooling at the surface and one of net heating at the stratosphere. They also contribute to other changes. Major change occurs in terms of the depletion of ozone, which we will see in the next few slides. So we take as a pointer the largest eruption of the 20th century, which occurred on 15 June 1991, namely Mount Pinatubo in the Luzon island of Manila, Philippines, 15° north and 120° east. It injected about 30 megatons of sulfur dioxide into the atmosphere. Now, the optical depth, familiar optical depth picture that we saw, this is only the stratosphere, which means 17 to 30 kilometers. This is the normal condition of optical depth in the stratosphere when there is no volcanic eruption. You can see that this is roughly about 0.001 to 0.01 during the normal conditions. But look at this, when the eruption occurred in June 91, you can see that the subsequent 3 months, you can see the optical depth increased by about at least 2 orders of magnitude, and the effect is global. Please note this point when we will revisit this in a few slides from now. So, as I mentioned earlier, that because of the reduction in the surface reaching shortwave radiation and absorption in the stratospheric long-wave radiation at the stratosphere, it will produce the sulfate aerosols or volcanic aerosols that produce a cooling at the Earth's surface. We can see that the Earth's surface cooled after every volcanic eruption in the history, and the stratosphere gets warmed by about 1 degree centigrade after the eruption. Also note that these effects are transient, meaning going up to 1 or 2 years after the volcanic eruption. So when I was discussing the other process, I also mentioned about these aerosols playing a role in ozone depletion. This again connects to the biogeochemical cycle distribution when aerosols contribute to the other aspects. As you are aware, the ozone depletion reactions take place on particles that provide surface areas for the reactions to occur, which are typically heterogeneous, meaning solid or liquid particle is the aerosol and the gases that are present. So these are in different phases, and because of this heterogeneous chemical reaction, ozone can can decrease. So it will produce ozone depleting substances from the chlorofluorocarbons, and these reactions occur on the aerosol surfaces. So in the background scenario versus a volcanically perturbed scenario, the major difference comes because of the following. There will be an increase in the number of particles in the stratosphere, and the second thing will be the increase in the size of the particle. So when the radius increases, as you know, that the area increases by r squared. So these heterogeneous chemical reactions can occur at much faster rate when the number of these particles and the size of the particles increase, which happens after every volcanic eruption in the stratosphere. So you can see the close correspondence where there is an aerosol increase. This is in the order of about 12 to 25 kilometers. There is a subsequent ozone decrease. So there is a close correspondence between the increase in aerosol with respect to a decrease in the ozone. You can see this effect in the global total ozone change. See that the large dip that occurred immediately after the Mount Pinatubo eruption, and is slowly started coming back to, trying to come back to the position that we know. So when we say climate change process or the components that make out of it, these include direct and indirect changes in the climate change drivers, which include the well-known greenhouse gases, aerosols, clouds, solar radiance, which contribute to radiative forcing, and then which can perturb the climate and the response, and through the human activities and also the natural influences, and the variation, the biogeochemical, the chemistry, the feedback process can actually change these drivers and also can change the climate perturbation and the response. So the global climate is influenced by the agents, the following agents that are present in the Earth's atmosphere, namely both are natural and the human-made. The long-lived greenhouse gases versus the aerosols. We know that the greenhouse gas warming is the major one which is contributing to the increase in the Earth's temperature, while aerosols, which are of different kinds as we know, can either warm the atmosphere or the surface or cool the Earth's surface. And you also see there is a large amount of error or uncertainty as far as the aerosols are concerned. So if you look at the global average surface temperature, look at the trend. For example, we are very well aware that the Earth has warmed by about in the last 100 years or so. Here we are looking at the trend per decade during the period. In the last 60 years, you see everywhere an yellow or a red spot that is. So what we do is, let us put the known causes of this contributing to global warming or increase in temperature. So let us put the natural causes, which is the changes in the solar irradiance and the volcanic eruption. So we know already, we have seen that after volcanic eruption, there will be the surface temperature will actually decrease vis-a-vis the regular time frame. So you can see that in the last 160 years or so, after every volcanic eruption, the temperatures have decreased. While the changes in the solar irradiance, which is minimal in the last 150 years or so, did not contribute to any change in the observed temperature. Then the immediate question is, come on, how is this happening? Now, in addition to this, let us add the greenhouse gases, aerosols, and ozone, the increases that have occurred in the last 150 years. You see, bingo, it happens. The model simulations match with the observations. So the influence of human emissions is unequivocal on the global warming or the climate. And you can see that the observed pattern or the simulated pattern with the natural and human forcing matches with the observed pattern. So in the last 150 years or so, the Earth has warmed by about 1 degree centigrade. The other effects of air pollution is it can reduce the incoming solar radiation by these particles settling on the leaf. We saw that be it scattering or absorbing, they can absorb or scatter. Hence, any radiation that would have come in the absence of this, they get reduced. And so it can reduce the photosynthesis, can reduce the productivity. So they can also increase the acidity and cause plant damage. So model simulations do indicate that there will be a decline in the yields that will occur due to the presence of aerosols in the Earth's atmosphere. Then the other very close effect that almost troubles everybody is the impact on the human health. We know that typically in the polluted, when we say polluted conditions, that the sky is hazy, etc. You can see the smell the air, as we call. So almost all the major metropolitan cities do have the aerosol concentration that is larger than the higher than the allowed limits because of the various activities that are there that is present over the region, and also due to the transport of the species depending on the dynamics, atmospheric winds, etc. So what all can happen? Health effects can range from decreased lung function to heart attacks, premature death, and almost everybody under the sun will get affected because of the pollution. Now, when we were discussing that the volcanic aerosols or stratospheric sulfate aerosols actually produce a cooling, then I'm sure one of them would have thought, one of the members in the audience would have thought that, well, man, you got a solution for the global warming. What you do is increase input the stratospheric sulfate aerosols or sulfate aerosols in the stratosphere, or reduce the amount of carbon dioxide in the atmosphere. So how the surface temperature will cool or the global warming will come down is because when the amount of radiation that is coming from the sun gets reduced because it gets reflected, so it will cause a cooling or it will decrease the temperature, or the amount of radiation that is absorbed with the long wave, it reduces, then also it will produce the cooling. So the common methods or the technology wherein we actually do what is called as the reverse engineering is also called literally geoengineering, meaning climate intervention. You engineer the climate to using the geography, everything. So you change the geostructure of the earth through engineering. That is called as the geoengineering, or also called climate intervention. So there are two methods with which you can achieve this one. One is the carbon dioxide reduction or removal, or the other one is through the solar radiation management. So you decrease the amount of radiation that is coming, receiving at the Earth's surface, then we know that it will produce a cooling. So let us concentrate on that by as a topic of interest today, with aerosols in the stratosphere being input into the Earth's atmosphere at regular intervals, then it will produce cooling. The other issues related to carbon dioxide removal or storage, it is a long drawn process, and also there are other effects and challenges. So for the time being, let us focus on putting the sulfate aerosols into the stratosphere. So here we are looking at the temperature anomaly, and then now in the last 50 years or so, and then let us inject an amount of sulfur dioxide and then varied amount of sulfur dioxide. So as you remember, I mentioned that Mount Pinatubo injected about an estimated 30 megatons of sulfur dioxide. So what we do is we split the amount of SO2 that needs to be injected, typically at 20 kilometer altitude, in terms of 5 megatons every 6 months versus 10 megatons every 6 months or so. And then look at the possible temperature change that will occur. These are from the model simulation and the model experiments those were conducted. So you can see in the last, what is in red is the global mean temperature anomaly, which is steadily increasing as we know. So we have touched almost on 1 degree, as I pointed out. So in 2020, for example. So now what we do is we begin this experiment in 2000 when we have injected 5 megatons of sulfur dioxide and 10 megatons of sulfur dioxide into the stratosphere, but you don't see much of a change in the initial time frame. And then 10 years later, so you have to keep this injecting regularly at every 6 months for about 5 years, and then see the effect on the temperature. So you can see that when the 5 megatons is injected, and you look at the temperature change after about 10 years, the Earth's surface has cooled by about 0.5 degrees centigrade. And with 10 megatons, it is actually almost touched zero, meaning offsetting the entire global warming caused by the greenhouse gases and the aerosols and ozone present in the Earth's atmosphere. We still go a little further, meaning 2020, this year, for example. So with 5 megatons of sulfur dioxide, the temperature decreases, but with 10 megatons, actually, we are even going lower than what we are experiencing now. Okay, and then 2030, you can see the effect that is happening. And now, let us try to see what happens if I extend this for another 10 years or so. But with a caution that I stop injecting the 5 megatons of sulfur dioxide and 10 megatons of sulfur dioxide into the Earth's atmosphere. Okay, I stopped from here to here. So what we see is that the green bar also has gone up and the blue bar has gone up, which was negative in the last 10 years. You can see the gradient that is happening. So in the last 60 years, you can see the gradient of the warming is kind of uniform and can be scaled. But look at because of the geoengineering or the climate intervention that we did, putting the sulfate aerosols which can cool the Earth's surface, you can see the gradient is much faster. Now this has serious consequences. What are they? So the only benefit that happens is that it reduces the surface air temperature, but look at the risks. For example, ozone depletion, we saw that it will deplete the ozone, which is equally important for the survival of the human health, for aquatic terrestrial ecosystems. These sulfate aerosols also will cause a drying of the atmosphere and will result in the drought condition. It will also change the composition of the Earth's atmosphere, so it will have an impact on the atmospheric chemistry. So it will warm rapidly, as we saw when the emissions of sulfur dioxide is stopped. And so with more and more of these particles, more scattered or diffused radiation will increase in the Earth's atmosphere, and this will have an effect on the ecological, right, on the ecology. For example, we know that more diffuse radiation on the leaf or the plant will reduce the photosynthesis. Now, more logistical questions, such as, which also has economic implications and societal implications, which is where and how do we inject this sulfur in the stratosphere? Now, in order for the global response, global change to occur, these aerosols need to be injected in the tropical belt. Then only the effects will be global, because they will diffuse across the latitude and the longitude, while injecting them at higher latitudes, namely in higher latitudes, will not result in a global response. Point number one. Second thing, how do you do it? Let us say that you can use a balloon, aircraft, etc. Aircraft means it has to go all the way up to 17 to 20 kilometers, and then we'll inject this sulfur dioxide, and you should do it regularly, as I said. So the question is the cost, who will bear, who will do that? And not only that, on the one hand, you are trying to control the global warming, but these emissions that are associated with the aircraft flying all the way up to 20 kilometers or so and transporting not 1 or 2, 30 megatons to 5 megatons of sulfur dioxide, okay, and then going and spraying there in the tropical belt. So you are kind of intervening with the climate, create the same scenario as a volcanic eruption would have produced or created, which means that will contribute to emissions that are already increasing. So there are more risks when compared to the benefits of this geoengineering. So I think I'm finishing up with the summary. So we looked at, for example, starting from water aerosols, the physics, chemistry, maths, biology, and the engineering aspects of it. How do we do it? What is it we do? What is it we study? Why they are important and the role they play in climate, and in what way doing anything by changing the concentration of these particles or sulfate particles, it will affect the Earth's temperature or in general the Earth radiation budget, etc. So thank you very much. I'm happy to answer the questions.
Thank you very much, sir, for such a comprehensive presentation. I think you have not left anything with, talked about aerosols. So thank you very much, sir, for such a wonderful talk. Now I request participants to please ask your questions or any comments, presentations to Ramchandran, sir.
Hello?
Yeah, please go ahead.
Sir, you said during a volcanic eruption, the temperature in the stratosphere increases. Why is that?
Because the sulfate aerosols will absorb the outgoing long wave radiation. And so, if you remember, the single scattering albedo of any species is also a function of the wavelength. In the infrared region, the single scattering albedo of sulfate aerosols is lower than 0.5 or so. So they can actually absorb the radiation. So when they absorb the radiation, they contribute to warming there.
So can they warm up even in troposphere then? Why is
troposphere? No, troposphere. See, as you are aware that the Earth atmosphere system is driven by the solar energy or the solar radiation that we receive at the Earth's surface. So in the Earth's surface, in the shortwave regime, sulfate aerosols are one which is of scattering kind. The single scattering albedo is close to 1. So they can only scatter the radiation. So they will send the radiation that is received back to space, and hence they will produce a cooling at the Earth's surface. And when you increase the number of sulfate aerosols in the Earth's atmosphere, as it happens after a volcanic eruption, you are increasing the cooling. So that is why after a volcanic eruption, in the surface or in the troposphere, the Earth's temperature decreases about 0.2 degrees centigrade on a global annual mean scale, but at the same time the stratosphere warms up by 1 degree. This cooling in the troposphere actually can vary as a function of region, latitude, longitude. Typically in the tropics, the cooling is higher than about half a degree, going up to 1 degree centigrade. So if you were there, I'm sure you are a 21st century kid. So just after, for example, the Pinatubo eruption, the winters after Mount Pinatubo, which occurred in June 91, was a little more colder because of the decrease in the surface temperature of about half a degree over the equatorial belt, including tropics, etc.
Thank you, sir.
Welcome.
Sir, I have one general question, sir. Compared to the present narrative of air pollution, particularly this relating to PM 2.5, and often using that as a parameter and say that is caused by transient events such as Deepavali crackers. So when we know that these aerosols are really a systematic process and also a lot of sources which are independent of an activity which happens, for example, once in a year. So is that really an effective, sir, compared to the many vehicular and other industrial emissions which actually do a lot of these things?
Okay.
Is any?
Okay. Okay. See, first is, for example, over an urban region, the amount of PM 2.5 particles that are present due to the normal sources of vehicular and industrial emissions is already existing.
Yes.
Now, this level itself, if you take the annual average, this level itself is actually higher than the national prescribed standards.
Yes, sir.
Now, during the Diwali or any other festival, what happens is you are increasing this significantly further to the already available threshold. So that is the reason. So, and since the conditions, for example, as it is happening in Delhi, for example, right now, the temperatures are so low. In fact, even in Ahmedabad, the sky is now hazy, cloudy. There is no sun at all. This is because the temperatures have become lower, and these pollutants that are emitted, actually they are not ventilated out because of the lower temperature and boundary effects. So then these are contained in this atmosphere. And the winds are also, the wind speeds. For example, I don't see any leaf now shaking here, moving here. So the aerosols produced over this particular city or region stays in that region. So compare this with, for example, during monsoon, you may be producing it, but the winds will sweep it away. So there is a mechanism to handle them. But in this time frame, like in winter and in post-monsoon, the prevalent atmospheric conditions actually add up to the increase that we are contributing because of these activities.
Thank you, sir. May I have another question, sir?
Sure, go ahead.
Related to retail of these AOT and kind of parameters, there are these both optical satellites and as well as these LiDAR-based technique. And also these days, a lot of these ground-based networks of these AOT stations, other things are there. And a lot of wireless sensor networking also. So compared to the LiDAR, is that optical technique is inferior in the way that they offer the quality, or are they better in terms of their globe and the coverage other than?
Okay, first thing we should understand is that LiDAR is used to derive the vertical profile,
Yes, sir.
while the other ones will give you the columnar concentration. We have, I think, the extinction that is derived, etc., from Calypso, which is the LiDAR in space, is quite good. That is being used to address several research problems. Even at the ground level, when you have a LiDAR that is fixed to the ground, the techniques, the errors or the uncertainty is actually very, very less. The one form of uncertainty creeps in when you try to derive the aerosol extinction from the total extinction, because you need to now assume that above 40 kilometers there were no aerosols or something, and then you try to derive the contribution of aerosols in the signal that you have seen. So this, for which you need what is called as a LiDAR ratio. Assumption of this actually contributes to this uncertainty in the LiDAR extinction. So what is typically done is, you can, in order to reduce this, you need to have a multi-wavelength LiDAR. So you can derive the size-dependent ratio, LiDAR ratio, and use it for retrieval. So wherein you can reduce the uncertainty.
So is that trend going to be, sir, because multiple LiDAR-based satellites are now, I think, going to come out. Is it better progress, sir?
Yeah, of course. Yes. Yes, we see, when the moment you say size distribution, say trying to identify fine versus squares, you need to have data at several wavelengths in order to derive, say, this one.
Thank you, sir. Thank you.
Any other question? So if you have any questions, you can post to me. I can pass to Ramchandran sir, and I think I'm sure that he will be able to give his reply of your questions. So if you have any later on also.
Yeah, sure.
So if there is no further question, then let us thanks Professor Ramchandran for his wonderful and informative talk. And thank you, sir, once again for agreeing our request. And
thank you for the invitation. Thank you. Thank you.
Thank you, sir. Thank you very much, sir.
Thank you.
Thank you, sir. Very nice.